Okay, looking now at question B3. This question is about the motion of a bicycle. A cyclist moving up a slope that is at an angle of 19 degrees to the horizontal. The mass of the cyclist and the bicycle is 85 kilograms. Calculate the component of the weight of the cyclist and bicycle parallel to the slope. Okay, the weight of the cyclist and his cycle is acting in this direction. That has a component, so this is mg equals 85 times 9.8. Yep. And there is a support force. So in fact, let's just show what the two components are of this one. So this weight force has a component that is this direction along the slope, and it has a component that is in this direction, perpendicular to the slope. And what it's asking for first is the green component, the component that is parallel to the slope. Okay, and that requires just a little bit of trigonometry. This angle here is going to be 19 degrees. And this side here, we can call the green side, we can call FG parallel. And FG parallel, well, it's going to be opposite over hypotenuse is equal to the sine of the angle. So FG parallel divided by 8.5 times 9.8 should be equal to the sine. So FG parallel should be mg times sine 19, which is equal to 85 times 9.8 times sine of 19. Using our calculator, we should be able to figure that out here. Let's clear that. 85 times 9. In fact, it's 9.81 that the IB likes to use, times sine of 19 is equal to 271. In fact, 270, because this is only to two significant figures. That should be a 1. So that's equal to 270 newtons. And then we want the normal reaction force on the bicycle from the slope. Okay, the normal reaction force is going to completely cancel out the weight force that is perpendicular to the slope. So the normal reaction force normal reaction is equal to FG perpendicular. Let's just label that in here so we know what we're talking about. This side here is called FG perpendicular. So the component of the weight that is pushing down on the slope, that's going to have an equal and opposite normal reaction force pushing up on the bike. Okay, so that side, so Fn is going to be equal to mg, well that's now the adjacent side instead of the opposite side, so it's going to be mg cos 19, and so let's work that out. It's 85 times 9.81 times 19 cosine is equal to 788, or 788 newtons, which is about equal to 790 newtons. We only want our answer to two significant figures, really. Okay. B. At the bottom of the slope, the cyclist has a speed of 5.5 meters per second. The cyclist stops pedaling and applies the brakes, which provide an additional decelerating force of 250 newtons. Determine the distance taken for the cyclist to stop. Assume air resistance is negligible and that there are no other frictional forces. Okay, so we want S. The first thing to note here is that the accelerating, or the total decelerating force, so F net, is going to be equal to 250 newtons, which was the additional decelerating force, in addition to the weight force slowing it down. So we already know that the weight force that is acting in that direction is 270 plus this additional braking force of 250, right? In other words, that's equal to Fg parallel plus F brakes. Okay, so that is equal to 520 newtons, and the acceleration of the bike is equal to, well, F equals ma, so it's going to be equal to F over m, which is 520 divided by 85. So 520 divided by 85 gives us 6.1 meters per second. Okay, so that's the acceleration. Then we actually want the distance taken for the cyclist to stop. So we're going to use, we know that v equals 0. That's the final velocity. We know that u equals 5.5. We know that a equals negative 6.1 meters per second squared, and we're wanting to find out s. The reason that a is negative is that the initial speed is up the slope, so if we decide that the initial speed is positive, then the acceleration must be negative. Okay, now we want the kinematic equation that involves those, which is v squared equals u squared plus 2as. V squared equals u squared plus 2as. Or if we rearrange that, we get s, which is what we're really interested in, is equal to v squared minus u squared over 2a, which is equal to, well, v squared is 0, so we get negative 5.5 squared over 2 times negative 6.1, which is 5.5 squared divided by 2 times 6.1. I'm just gonna, because there's a negative in the top and a negative in the bottom, I'm just gonna ignore the minus signs, and we get a distance of 2.47. Does that look right? 2.47, actually 2.5, we'll say. 2.5 meters. Okay. B4. A student uses an electronic timer in an attempt to estimate the acceleration of free fall. This is another data analysis question, really. Using h equals half gt squared, calculate the expected percentage uncertainty on the value of g. To do this question, let's just first rearrange this. So g is equal to 2h over t squared. So what we're really doing is 2 times h divided by t divided by t. So when we're multiplying or dividing, we add the relative uncertainties. And when we multiply this by a number, that doesn't affect the relative uncertainty at all. Okay, so we get the uncertainty, the relative uncertainty in h is 0.6. So we get 0.6 plus 0.3 plus 0.3 will give us the total relative uncertainty, which is 1.2%. And we usually state these uncertainties to the nearest, well, just to one significant figure, is about 1%. Okay. State and explain how the student could obtain a more reliable value for G. We kind of need to look at what they did. They used an electronic timer. They measure the time taken. The percentage uncertainty in the measurement is that. They've fallen through a height. So they would have measured the time, measured the height, and it's based on those. So the most important one, because it's squared, is to improve the accuracy of the time. And that can be done by repeating the measurement, for example. Or, I mean, that would improve the reliability of the value. So, the timing is most important, as it is squared. I mean, we saw when we dropped that volleyball in the atrium that actually the small differences in time led to a huge uncertainty. So the timing is most important as it's squared in the equation. It can be made more reliable by repeating the measurement. So many of you wrote that you could have multiple people timing the same event, and that's kind of what we did out in the atrium, and that's equivalent to repeating the measurement. Okay. We could also get a more accurate time if we had a longer height, because that would mean that the time that we're measuring is longer, which means that the kind of response at the start and the response at the end would have a smaller impact. So increasing the height would also increase the time. Reducing the impact of uncertainties in timing, because those uncertainties come mainly from the starting and stopping of the stopwatch, and so if we had a longer time to measure, then our measurement of the time would be more accurate. Or we could also reduce air resistance, which could be done either by a smaller ball, or, which would be kind of difficult, you could do the experiment in a vacuum, or experiment in a vacuum. Okay, which is not really that feasible. But if you had the gear, then you could possibly do it. Another approach that the Mark schedule takes is that you could do an experiment with different heights and then get a line of best fit and then use your gradient to work out what half g is, the gradient of a graph of h against t squared. Okay, so that's an alternative method, and that's why we do that kind of experiment with the gradient to get the equation. All right. B5, and I think this is the last question. So cars I and B are on a straight racetrack. I is moving at a constant speed of 45 meters per second, and B is initially at rest. As I passes B, B starts to move with an acceleration of 3.2 meters per second. Okay, and there's our diagram of it. Okay, at a later time, B passes I. Show that the time taken for B to pass I is approximately 28 seconds. Okay, so what we want is to work out at what time they've both traveled the same distance. Right, because if they've both traveled the same distance from the starting time, then they'll be passing each other. That's the time at which they pass. Okay, so let's do that. So for the car traveling at constant speed, relating the distance and the time is not that hard, because for car I, v is equal to d over t. So d is equal to vt is equal to 45t. So that's an expression in terms of time of how far I has traveled. For B, this is uniformly accelerated motion. We know the initial speed. We don't know the final speed. We want the distance in the expression, and we want the time in the expression. And do we know the acceleration? I think we know the acceleration. Let's have a look. We do know the acceleration as well. So we want an expression with u, t, s, and a, and the kinematic equation that relates those, u, t, s, and a, is s is equal to ut plus half a t squared, and u is 0, so that part cancels out. So for this one, in fact, I'm just gonna because I want to use the same notation for both. I'm going to call this s as well. That's si. Whoops. Just to make things neater. So therefore we get SB is equal to a half times 3.2, which is 1.6, 1.6 t squared. And they will pass each other when SI is equal to SB. So we have, or i.e., 45t is equal to 1.6 t squared. Okay, and we can cancel one of the t's here. So divide both sides by t. So we then get t is equal to 45 over 1.6, which is equal to, hopefully, approximately 28. It looks promising. 45 divided by 1.6, 28.125. Which is approximately 28 seconds. Okay, so that worked out nicely. Calculate the distance traveled by B in this time. Okay, we can just use the equation that we got from the previous question, which is this one. I mean, this is going to be the same for I or B, so you could use either one really. So we can say S is equal to half a t squared, which is equal to, I'm going to use the unrounded number, 28.125. I don't know if the mark scheme did that. So S is equal to a half times 3.2 times 28.125 squared, which gives us 0.5 times 3.2 times 28.125 is equal to 45. 45 meters. That doesn't look right at all. Let's have another look. Let's try that again. 0.5 times 3.2 times 28.125 squared is 1.265. That looks more correct. So this, I think I forgot to square it. Okay, so let's try that again. That is 1.265 times 10 to the 3 meters, which is about 1.3 kilometers. Okay. Finally, B slows down while I remains at a constant speed. The driver in each car wears a seatbelt. Using Newton's laws of motion, explain the difference in the tension in the seatbelts of the two cars. So I is in equilibrium. Driver is also in equilibrium. So no force is acting on driver of I as Newton's first law says that objects, oops, there's no apostrophe needed there. Let's get rid of that. Can't have that. As objects, Newton's first law says that objects moving at constant speed a constant velocity have no net force. Okay, so there's no real so no tension required in seatbelt. I mean, except for the tension that kind of holds it in place. Okay, B is decelerating. Seatbelt must produce a retarding force on the driver to slow him or her down. Hence, by Newton 2, F tension must be equal to m driver times A. Okay, that should be enough to get us the 3 marks. You can double check it against the marking schedule. It's not the most efficient phrasing of it, but you can check. One thing I should say is that my writing is kind of big with this red pen. In your exams, you should never go outside the box like this, because that you run the risk of anything outside the box not being marked. So if you find you run out of space, you have to ask for the special extra paper and write your extra answers on that paper. Okay, a third car, O, with mass 930 kilograms, joins the race. O collides with I from behind, moving along the same straight line as I. Before the collision, the speed of I is 45, and its mass is 850. After the collision, I and O stick together and move in a straight line with a combined speed of 52 meters per second. Calculate the speed. So we'll say the speed of O before the collision. So using conservation of momentum, we have Pi is equal to Pf, and we have all the information about the final situation, so let's work that out. Pf is equal to, they stick together and move in a straight line, so it's mass times the speed, or mass times the velocity really. So Pf, the total mass that's moving is 930 plus 850 times the speed of that they're moving is 52, which is equal to, so 930 plus 850 equals times 52 is equal to 92,560. 92560 kgms to the negative 1. Okay, so that's the final. P initial is equal to, well, we know that before the collision I has a speed of 45, so it's going to be 45 times the mass of car I, which is 850, plus V of O times the mass of O, which is 930. Okay, and then I'm going to go back up here. So we get 930V. Well, in fact, let's just go straight into writing an expression for V. So we have VO is equal to PF is equal to PI, so it's going to be equal to 92560 minus 45 times 850. 92560, that's the total final momentum. And we want to subtract from that the initial momentum of the other one, which is 45 times 850. And we want to divide that by the mass of O, which is 930. And so that should give us the final speed. So we have 92560 minus 45 times 850 gives us 54,310, and then we want to divide that by 930. And so the speed of that car is 58.39, or 58 meters per second. Okay. And then finally, the duration of the collision is 0.45 seconds. Determine the average force. Okay, so F average is equal to the change in momentum divided by the change in time. Okay, O's change in momentum. So that's going to be equal to O's final momentum, which is 52 times 930. Because at the end it's moving at 52 meters per second, minus the initial momentum, which is 58 times 930. And then we're going to divide that by 0.45. Okay. So 52 times 930 minus 58 times 930. oops, not divided by. So 52 times 930 minus 58 times 930 equals, and we're going to divide that by 0.45. We get negative 12,400. Or 12,400 newtons in opposite direction to motion. Okay, cool. So that's the last question of the mid-year exam. Any questions that you have, or any parts of this that were unclear, we'll go over in detail. If you just request it, we can go over that on Wednesday. All the best, and I hope that these videos were clear and helpful.